So we're moving on from Gauss's law to talk about something completely new, which is electric potential. When you hear electric potential, I want you to know that in everyday speech, this is usually what we refer to as voltage. And so when we're talking about the voltage, like what comes out of a battery or what comes out of a plug in your home, what we're really talking about is electric potential or electric potential difference. So that's one of the things that I wanted to just mention. As we go through this chapter, it's important to make sure you understand the vocabulary. Specifically, I've put 3 terms here just to get us started: electric potential energy, electric potential difference, and electric potential. Those 3 things are all different. So as we go through the chapter, make sure that you understand the difference between these 3 terms, okay? So you'll notice that only one of these is an energy, and these 2 are something new. To get you motivated for what we're doing next in the course, I want to just kind of show you where we are this semester and compare it with where we were last semester. If you think about how we studied mechanics, which is, again, the physics of motion, if you think about how we started the course last fall, we started with a force approach. In other words, first we studied kinematics, we figured out, how things move, and then we used Newton's laws of motion to figure out that it was forces that caused acceleration or changes in motion. We also talked about the universal law of gravitation, talked a little bit about the concept of a gravitational field, but not very much. Well, this semester, as we've started our study of electricity, we've also been using a force approach. So first of all, you'll notice that we've used some kinematics and Newton's laws of motion. Instead of the universal law of gravitation, we saw that we have Coulomb's law, which is mathematically equivalent to the universal law of gravitation. And we've also spent a lot of time talking about electric fields, and that's equivalent to gravitational fields. So we found that if we know there's an electric field in a region of space, the electric field exerts a force on our charge, F equals QE, and then we can use kinematics and Newton's laws to figure out things. The one thing that's kind of been new this semester is we spent the last chapter on Gauss's law. We didn't see any equivalent for that last fall. Well, last fall, what we did after we spent the first month or 2 using a force approach is we then used a completely different approach, and that's the energy approach. So we defined what energy was. We talked about kinetic energy. Kinetic energy obviously is going to pertain directly here, because whether it's the kinetic energy of a cannonball or an electron, it's the same thing. So that's just going to be the same. And then we talked about gravitational potential energy. So in this chapter, we're going to start looking at energy in electricity. So electric potential energy. It's just going to be essentially the same thing for electricity as we saw in gravitational potential energy. But then I want you to notice there are these 2 terms, electric potential difference and electric potential, which we did not have an equivalent of last fall. So those are going to be completely new concepts. It turns out in higher levels of physics there are equivalents for gravity. We just don't do it at this level. Now, all the good stuff that you remember, hopefully, about conservation of energy is still going to apply for electricity. Effectively, we just have to know what is delta U. In other words, it's not gravitational potential energy anymore. It's going to be electrical potential energy. But otherwise, conservation of energy is going to apply just like it did before. So let's keep going with our review. Let's look at the work energy theorem. The change in kinetic energy plus the change in potential energy is equal to the work done by non-conservative forces. So remember, NC stands for non-conservative. And what do we mean by a non-conservative force? Can you think of an example of one? Well, hopefully you can. Hopefully there were 2 that you remember from last semester. Friction is an example of a non-conservative force. And then also applied forces. Now, I wanted to remind you just what do we mean by that whole work term? Remember that that's basically how we get energy into or out of a system. If you do work on an object, you're either giving the object energy or you're taking energy away. So generally an applied force is how we give an object more energy than it has before. We know friction always takes energy away from an object. It turns out that for most of the problems we do with electricity, this is going to be zero. Okay, so for most of the problems we do, that's going to be zero, really for everyone. Kinetic energy, I've just reminded you of the formula for kinetic energy here. Gravitational potential energy, remember if an object is at a height y above the Earth, then it has a gravitational potential energy equal to mgy. More generally, if we're far away from the surface of the Earth, so here's the Earth, and our object is up here, remember we have to use this more complex formula for gravitational potential energy. So those are things that we talked about last fall. I want to talk a little bit more about work and remind you about the definition of work. When we defined work, we defined it as the dot product of the force and the displacement. Remember, the way we calculate a dot product is we take the magnitude of the force, the magnitude of the displacement, times the cosine of the angle between them. Okay, so here's theta, here's delta r down here, and here's f. Remember, when we say magnitudes, we mean positive, so these are always positive. Now, it turns out that if the force is not constant over the displacement, then we have an integral definition for work. This is often called a line integral. And basically, this is something that really you don't see until Calc 3 because it's a vector product in there. But basically, it's no different than an integral you would do in Calc 2. You just first rewrite it as f dr cosine theta, and then solve it just like an integral you would do in Calc 2. Fundamentally, all we're talking about here is that if I plotted the work, or if I plotted the force versus the displacement, the work would simply be equal to the area under that graph. All right, I next want to remind you about what we mean by potential energy. So here's the definition we used last fall. We said the change in potential energy associated with a conservative force is the negative of the work done by that force as it acts over any path from point A to point B. The key thing to remember about a conservative force is that the work done by the force is independent of the path taken. That's the important thing. And so when we define the change in potential energy, we define it as minus the work done by the force. The good news is the electrical force, just like the gravitational force, is conservative, and so we're able to use potential energy when we're dealing with electricity. I want to remind you of how we got to our current version of the work energy theorem. Back in chapter 6, the work energy theorem that we had was that the change in kinetic energy was equal to the net work done by all forces present. Okay? And what we did then was we said, let's separate out the work done by conservative forces like gravity and keep those separate from the work done by non-conservative forces. Then what we did was we said, we can define the change in potential energy as minus the work done by a conservative force. So instead of the work done by gravity, we had minus the change in potential energy for gravity. And that's what ultimately led us to delta K plus delta U equals WNC. And so really our next goal is we got to figure out what is delta U for the electrical force, just like we found what delta U was for the gravitational force. before we get into the details of that, I just want to argue that there should be such a thing as electric potential energy. We know that if you have a mass in a gravitational field, it has potential energy. And the way we know that is if you take this object and you let it go, it gains kinetic energy. If it's gaining kinetic energy, it must be losing some other type of energy, and that's gravitational potential energy. By the way, which of these objects has a greater gravitational potential energy? Okay, so I bet some of you yelled out they have the same, and they don't. Remember that gravitational potential energy does depend on the mass. So in other words, it's mgy. Well, the bigger mass has greater gravitational potential energy. Notice that as they get to the bottom, the bigger one also has more kinetic energy. But when you solve for the final velocity, the velocities are the same because the masses cancel out. Okay, so we know these objects have gravitational potential energy because if we let them go, they're going to fall. They're going to do something. Well, in the very same way, we know that these objects have electrical potential energy because if I take a positive charge Q and I let it go by in between these two oppositely charged plates, we know that that charge is going to accelerate in that direction. If it's gaining kinetic energy, it's got to be losing some other kind of energy, and that's electrical potential energy. We'll also have to kind of figure out, does this have more electrical potential energy than this one does, in the same way that the big mass has more gravitational potential energy. All right, so let's do an example, and we'll do the simplest example we can. So the example is, how much potential energy does a positive charge gain when moved from point A to point B in a constant electric field? So first of all, I want you to understand that this is completely equivalent to asking how much gravitational potential energy this mass gains as I raise it up in a gravitational field. Okay? So we know that if I take a mass and I raise it up in a gravitational field, the change in potential energy would just be mg delta y. So let's see what we get when we do it in the case of an electric field. So first of all, notice that we want to move opposite the direction of the field. So delta r is a vector in that direction. We can see the electric field is in that direction. So notice the angle between E and delta r is 180 degrees. So in this case, since the electric field is constant, I can go back to our simpler definition of work, that it's just the dot product of F and delta R. Excuse me. And so I get F delta R cosine theta. Remember that F and delta R are magnitudes. And so we get negative F delta R. We've got the cosine of 180. We also know what F is for a charge in an electric field. It's QE. So we get QE delta R, because you'll notice cosine 180 is -1, so that cancels out the negative sign. So we ended up with delta U equals QE delta R. And I want you to notice that that is completely equivalent to the gravitational situation, because instead of M, we have Q. Instead of the electric field, we have the gravitational field, or acceleration due to gravity, and then how much we are moving it in the field. All right, we're now ready to meet the new thing, which is electric potential difference. By the way, that language, electric potential difference, we could also say it as change in electric potential. So notice the way we say delta U is change in potential energy. We could say that stands for potential energy difference. So it's just kind of a different way of saying that. But the way we define electric potential difference is it's the potential energy difference per unit charge. Okay, so it's delta U divided by Q. Notice that our symbol for electric potential difference is delta V, or V is our symbol for electric potential. Now, why it is that we want to take potential energy and divide by charge in the first place, that's something that I'm going to explain to you as we go along. But for right now, let's look at how this new thing, electric potential difference, can be related to the electric field. First of all, I want you to notice that electric potential difference is a scalar, and that's important. That simply means it's much easier to use than a vector is. And remember, that's kind of one of the main advantages of the energy approach is it's scalars instead of vectors. All right, so I want to rewrite potential energy as the integral of F dot dr, as we've talked about, as we go from point A to point B in our electric field, and divide that by Q. Well, we know that F over Q is the electric field, right? That's our definition, in fact, of electric field. And therefore, I can rewrite this as the integral of E dot dr from point A to point B in the field. So fundamentally, electric potential difference is related to the underlying electric field. If the electric field is constant, then as usual, we don't have to do the integral, and we can just say the electric potential difference from point A to point B in the field is just minus E dot delta R. Okay, so that usual equivalence. And of course, to actually calculate that, I just take the magnitude of E, the magnitude of delta R, and multiply by the cosine of the angle between them. All right, so I want to justify why we're even doing this, but before I do, let's look at the unit for electric potential difference. Well, from our formula that by definition, the electric potential difference from point A to point B is the change in potential energy from point A to point B divided by the charge. Well, we know that potential energy has units of joules, and we know charge has units of coulombs, and so electric potential difference has units of joules per coulomb. Now, because electric potential difference is very important, it gets its own unit, which is V, which stands for volts. By the way, notice it's maybe a little bit confusing that V is both the unit and the symbol in this case. So V is electric potential, delta V is electric potential difference, and the unit is V for volts. All right, so let me try to justify why we have this new thing called electric potential difference and why it might be useful. So as I say on the slide, we could have defined gravitational potential difference last fall. We just didn't. By the way, you do in higher levels of physics. So this is actually something we really do. But the idea is if we were going to do it for gravity, instead of dividing by Q, we divide by M. So let's look at what would that gain for us? What would the point of this be? We mentioned a few minutes ago that these objects do not have the same gravitational potential energy. The bigger mass has more gravitational potential energy. But there is something that's the same for these two objects as they fall from there down to here. And what that is the gravitational potential difference. Because you'll notice that if we divide by M, we end up with delta V would just be G delta Y. So in other words, no matter what mass you put right here, if that object falls down to here, the gravitational potential difference it goes through is the same for both. Okay? So it's really what is the underlying thing that's the same for both of those masses as they go through that motion? Well, it's the gravitational potential difference. So for electricity, we want the same kind of thing. What is the same for these two charges as they go from where they are to another location in the electric field? And it turns out that both of those charges will go through the same electric potential difference. Now, the reason this is so important in electricity is it turns out the electric potential difference is the thing we usually know. In other words, you're going to see we're going to be doing problems where we're going to say, connect a battery across these two plates of 1,000 volts. Well, that is the electric potential difference between the two plates. So in other words, that's the thing we usually know in an electrical problem. We know the electric potential difference, and then we can use that to calculate the change in potential energy for any particular charge. All right, this is a really important slide. I'll put some stars on it just to remind you, like we usually do. And that is, I want to make sure you understand the relationship between the charges on these two plates. And again, right here, I'm denoting two parallel plates, like we've talked about a lot in class. And I want you to understand the relationship between the charge on the plates, the electric field between the plates, and the electric potential difference between the plates. Okay? One of the important things to notice in our definition of electric potential difference and how it relates to the electric field is that there is a minus sign. Okay? So that minus sign is important. It means that the potential difference increases opposite the direction of the electric field. So for example, if I tell you that this plate is positively charged and this plate is negatively charged, we know from previous learning that the electric field would go to the left. So notice if I actually took a charge and moved it from point A over here to point B, that would be the direction of dr. So our integral would be positive, but we've got the negative sign out front. So that would be a negative electric potential difference. So in other words, if this plate is at 5,000 volts, this plate would be at 0 volts. And so that charge would be going through an electric potential difference of negative 5,000. In other words, delta V would be, delta VAB would be 0 minus 5,000, or negative 5,000 volts. Okay, so remember, if you know which plate is positive and which is negative, you can tell the direction of the electric field, and you can also tell which plate is at the higher potential, because if you go in the direction of the electric field, the electric potential difference you go through is negative. By the way, you actually saw this in the equipotential lab that we did right before vacation, that the electric field was in the direction of decreasing electric potential. All right, let's look at the type of problem we can now do with our newfound knowledge. Notice, by the way, when I write the work energy theorem now, I'm setting the work done by non-conservative forces equal to 0, because we're not going to have any non-conservative forces. So the problem says a proton is released by the positive plate and a voltage across the plates is 6,000 volts. What is the velocity of the proton when it reaches the negative plate? Now, if I had given you the strength of the electric field in this region, you already know how to do the problem, because that's the force way to do it. But now we're going to do it with the energy way. The other thing I want to point out is, although this is our definition of electric potential difference, when we use that formula, we almost always use it in this way, which is we know what delta V is, and we're trying to find out what is the change in potential energy for a charge Q that goes through that electric potential difference. Okay, so that's almost always how we actually use that formula. All right, so let's figure this out. The first thing we want to do is just figure out what is the electric potential difference as I go from point A to point B. Well, that's just the final electric potential Notice how I'm using the terms electric potential and electric potential difference. So it's the final electric potential when the charge gets over here minus the initial electric potential. That's the electric potential difference. In this case, we end up at 0 volts. We started at 6,000 volts, so minus 6,000. And therefore, the electric potential difference we went through is negative 6,000 volts. All right, once we have that, we can now figure out what is delta U. Well, the change in potential energy as the charge goes from point A to point B is just Q times the electric potential difference that it went through. And in this case, it's an electron, or sorry, it's a proton, so the charge is 1.6 times 10 to the negative 19th. And I multiply that by negative 6,000. So the change in potential energy is just negative 9.6 times 10 to the negative 16th joules. All right, once I have that, now I can just use my conservation of energy formula. I know delta K plus delta U is equal to 0. And by the way, the AB is just reminding you that you're going from point A to point B. I'm going to drop it at this point for the rest of the problem, but don't be confused by that. We're just explicitly saying we're starting at point A and ending at point B. All right, so delta K is equal to negative delta U. Okay, so we had delta K is equal to minus delta U. This particular problem, well, in any problem, we know delta K is just the final kinetic energy minus the initial kinetic energy. And in this particular problem, we know that the initial kinetic energy is 0 because V naught is 0. By the way, one thing you have to be really careful of here is understanding what V we're talking about. Little or lowercase v, velocity. Big V or uppercase V, electric potential. All right, so in this problem, we can get rid of the initial kinetic energy. So let me just go ahead and solve for V. So V is going to be equal to the square root of negative 2 delta U divided by M. And now we can plug in our values. You'll notice that even though we've got that negative sign under the radical, that's going to be okay because delta U was negative. So we have negative 2 times negative 9.6 times 10 to the negative 16th. And dividing that by the mass of a proton, which is 1.67 times 10 to the negative 27th kilograms. And what we get when we work that out is we get 1.1 times 10 to the 6th meters per second. Okay, so that's the way we do a problem like that with energy. Again, really the only thing that's different about this than if we had done this back with gravity is that what we know or can easily determine is the electric potential difference. And so once we have delta V, then that allows us to find delta U, and now we just plug in to the work energy theorem. Okay, so that's the method. And I'm going to have you guys try one here in just a minute. First, I want to show you a simulation, which is about an electron gun, and I'll bring that in right now. An electron gun is what is in the back of any old-fashioned television or computer monitor. And basically the way TV used to work is that there is this electron gun in the back of the TV. It shoots a beam of electrons at the screen, and on the inside screen is there's a coating of phosphor atoms. When the electrons hit the phosphor atoms, they give off light. And so basically by having the electron beam sweep back and forth across the screen and alternating how intense it is, that's how the picture was drawn on the front of an old-fashioned TV. So here's what's at the heart of an electron gun. The first thing we have here is the filament. And the filament is just like the filament in an old-fashioned light bulb. If I put a voltage across that filament, what happens is it heats up. And if you could see this in real life, you'd see it would start glowing red. And so we know it's hot, and therefore electrons are being released from the filament. And they're just kind of essentially boiling off the filament is usually how we refer to it. Now what I want to do is I want to put a voltage difference between the filament and this conductor here, which has a hole in it. And as I put a positive voltage across that, then you'll notice what that's doing is it's creating an electric field in the opposite direction. And therefore my electrons, since the electric field is to the left, my electrons are going to accelerate to the right. And by changing the voltage here, I can change how fast the electrons are going when they exit the electron gun. All right, here is a practice problem for you to do. See if you can work this out based on the problem that I did with a proton. It's really the same problem, but now we have an electron. And I want you to try to carefully work it out and see what you get, and then restart the video and I'll show you what I got. All right, so here's how we would do the problem. Again, the thing that we can figure out easily is the electric potential difference that the charge goes through. Here we have to be a little bit careful. You'll notice that delta V, or what we say delta VAB, because I'm saying that's point A that it's starting from, and point B is where it's ending up. That's going to be the final electric potential minus the initial electric potential. In this case, notice the final is 6,000 and the initial is 0. So our electron goes through a positive electric potential difference of 6,000 volts. Now we would find the electric potential energy change, or delta U. Well, that's just Q times delta V. But notice that even though the electron went through a positive electric potential difference, we know conceptually it's got to be losing potential energy if it's gaining kinetic energy. And you'll notice that's exactly what we find, because now, although delta V is positive, Q is negative. So negative 1.6 times 10 to the negative 19th is our charge. Our delta V is still 6,000, and we end up with negative 9.6 times 10 to the negative 16th joules. You'll notice that that's the same electric potential, or change in electric potential energy, that our proton went through in the other problem. What makes this different is just I wanted to make sure you notice that delta V was positive, but delta U was still negative as our electron went through this acceleration. Once we've got that, the problem goes just like the other one, so I'll just cut to the end. The velocity, and again that's V for velocity, would be minus 2 times delta U that we just figured out, divided by the mass. And if you plug in the mass of an electron and do that, you should get 4.6 times 10 to the 7th meters per second. Okay, so again, notice what we did. We went from delta V, electric potential difference, we figured that out first. Then we found the change in potential energy that that particular charge went through. And then finally, we used the work energy theorem.